Hi everyone, I'm Yanlong, a PhD student in the Sustainability Geophysics project. This video will discuss a non-destructive set investigation using information from the surface wave. Since shear wave velocity is an essential factor correlated with the soil strength and stiffness, we propose a new data processing framework to extract underground shear wave velocity profile based on the back calculation from the finite element simulation. Now let's have a quick review of how to conduct the seismic site investigation, which mainly includes 4 sections: field acquisition, data transformation, set up the forward modeling, and model inversion. First, we went to the field, deploy the geophones according our acquisition design, and create the active sources from a sledgehammer. For more field acquisition information, please refer to the science video in our channel. When waves propagate through the underground, each receiver detects the ground vibration and records information of the soil particle velocity. Combining all the geophone recordings, we obtain the shoot-gather figures that contain the wave field information in this region. Soil profile can be obtained by interpreting the signal from the receivers. We convert the raw data into the frequency and phase velocity domain with a 2D fast Fourier transform and a fundamental wave propagation relationship. That is, the wave velocity equals to 2 pi times the frequency divided by wave number. Finally, we obtain the dispersion spectrum, which is the critical step for our analysis. We will discuss more on this later. The partial differential equation system is established to simulate the wave propagation in a solid medium. We use the finite element approach to solve this physical problem as a forward operator that discretizes the model in spatial and time domain. We then extract the theoretical shoot-gather that follows the in-situ acquisition parameters, calculate the dispersion spectrum, and compare it with our field observation. Previous to our last video, we discussed how to simulate the seismic wave using the finite element method. Please refer to the video, Simulating Wave Propagation through the Recycled Soil for more information, following the link below. The fourth part is the model inversion. This procedure requires updating parameters so that the theoretical dispersion spectrum and field observation finally become consistent with acceptable error. Our research establishes a surface wave inversion workflow to stratify the soil layer in shear wave velocity using a more accurate forward simulation, a more robust and convex objective function, and a more efficient optimization strategy. Now let's move to the method section. After obtaining the theoretical dispersion spectrum, we compare its similarity to the field observation and following the consistent distance criteria. We then update the model parameters using the Bayesian optimization to minimize the divergences of the two spectra. We propose a new way of using the consistent distance as the objective function to measure the difference between the finite element theory dispersion spectrum and field observation. How to do this? First, we slice the dispersion spectrum to obtain the phase velocity distribution at each frequency. As shown on the left, we compare the distribution difference between the field and FEM data via objective function and sum them up along all frequency bandwidths to obtain the final value. Why do we need the consistent distance as objective function? Let's compare it with the conventional mean square error method. For simplicity, assuming that the two identical phase velocity distribution needs to match with each other, the only difference is the phase velocity shift. We move the signal from the left side to the right side, and then calculate the objective function at each position. The original signal is shown in a solid black line, whereas the blue and orange line represent the noisy spectrum after adding 10 and 30% uniform noise to test the robustness. We plot the normalized consistent distance and MSE against the velocity shift shown on the right. The consistent distance-based objective function does not vary with the significant noise. Plus, the objective function also shows the convex property. Hence, it is found that consistent distance-based objective function is more robust in the noisy dispersion spectrum, and it is smooth convex properties compared to the MSE, where the latter shows the thermolocal minimum. After calculating the dispersion spectrum difference, we are going to back calculate the model parameters with minimizing the objective function fx. This procedure is known as the inversion. Of course, we will not blindly search for the solution. Instead, the Bayesian optimization strategy is employed for inversion. Recall the fundamental Bayesian equation. Posterior equals to likelihood times prior. The posterior is the actual objective function, which we usually don't know too much about it since it is very complicated. But we can replace it with the circuit model. Although not strictly required, we can assume the objective function follows a Gaussian precise, whose joint probability follows multivariate Gaussian distribution. Given that observation contains x and fx, we can condition our distribution on data as a mean function plus a standard deviation function. In this animation below, the red area represents the ground truth, the green area is a surrogate model. As we can see, the surrogate model gets closer to the actual function when more query points are generated. The selection of the following query points relies on the acquisition function, which can be calculated from the current posterior. We use an expected improvement as an acquisition function, as shown in the figure on the right. The query point is selected as the position of the maximum the expected improvement, so we calculate the objective function at this point and update it to the posterior. This procedure will continuously repeat until the objective function reaches the satisfying value or it stops when the iteration reaches to the limitation. Four parameters influence the elastic seismic wave propagation: shear wave, P wave, density, and layer thickness. Since the shear wave velocity is the most sensitive parameters to the dispersion spectrum, we focus on this value here in the inversion procedure. Now we have discussed all of the critical elements in inversion, including the persistent distance, objective function, and Bayesian optimization. So how is the performance of our new framework? We test our framework on the synthetic data. We simulate a particular three-layer soil structure that contains a low-velocity layer. Such soil profile generates a complex shoot gather due to the soft layer as shown in the upper left. Correspondingly, the multimode radial waves also appear in the dispersion spectrum after the domain transformation, illustrated in the color in the upper right figure. Usually, it is challenging to determine the mode of each energy block in this dispersion spectrum for the near-surface characterization. We apply our method to retrieve the shear wave velocity profile. After 80 iterations, the inverted dispersion spectrum with an energy of more than 40% is plotted by white contour lines, which agrees reasonably well with the background. Refer to the inverted shear wave velocity profile shown in the lower left. It is very close to the known profile at the first two layers and only with a very small divergence at the third layer. We then plot the surrogate model. The diagonal shows the effect of the single parameter on the objective function, and the off-diagonal plots demonstrate the impact of the two varying parameters. This figure indicates the sensitivity of each parameter to the objective function. We observe that shear wave velocity in layer 1 and layer 3 are less sensitive than in the second layer, attributed to the limited high and low frequency information available in this spectrum. Shear wave velocity of the second layer is the best constraint parameters with the narrowest defined minimum of the objective function. Our new framework can automatically update the model parameters that do not require the objective judgment, hence reducing the risk of the manual misinterpretation. Now let's step into the conclusion part. Persistent distance objective function exhibits a more robust and convex feature compared to the conventional MSE. The Bayesian optimization provides an automatic and effective strategy for dynamic FEM inversion to profile the underground. Synthetic data shows the promising future of the data-driven geophysical set investigation in engineering communities. However, further industry applications still need the field data verification that calls for the workflow optimization such as hyperparameter tuning and specifying the bounds of the model space. The authors would like thanks to NUS Deltra's collaboration for sponsoring this video. We are from the Sustainability Geophysics Project. If you are interested in urban geophysics topics, please find more on our webpage We will regularly update our research on the YouTube and Bilibili channel. Please subscribe by following the link below. Thanks you guys for watching. See you in the next video.